Hello everyone, this is your first lecture for book problems. This is chapter 3, scientific measurement. Remember, you're doing the odd problems from the book version, which is very close to this version, but there are some problems that are slightly different and better. Make sure that you take some notes. Remember that you can take notes and use them on your outline, and which can be used for your test. So the first bunch of slides will go very quickly, so let's get started. Count the significant figures in each length. There are rules for significant figures on the lecture. You may want to look at those. It's very important. So that's 4 significant figures. The last 0 means that the point is right on the 3. The first 0 to the right of the decimal is a placeholder. And the first 0 period to the left of the decimal is just a formatting 0. So that's 4. This is 4. Remember, all non-zero numbers are significant, so there's 4 there. I'm kind of going through the rules a little bit. There are, I think, 6 rules listed, so there's 4 there. I should put the answers a little bit more quickly. Why don't I put this on pause just for a second? After I do this one, you'll never know I was gone. There are 2, because the first one is a formatting 0, and the next 3, the first 3 after the decimal point, are to keep the place value. So there are 2. Okay, so the next one is going to be 5, because any zeros between 2 significant figures. Remember, non-zero numbers are always significant, so that's 5. Let's look at the next one. How many significant figures are in each measurement? Again, we're going to work on significant figures. Remember the 6 rules. You may want to have them open while you're working, maybe take notes on them so you have them on your test. All non-zero numbers are significant, so there are 3 significant figures there. Next, you have, there's 3 there, and then there are 2 there, because the first 0 is formatting, and the next 0 is a placeholder. I'll talk about formatting zeros. Ask me about that, and I'll let you know. Extra credit if you ask me. So there's 2 there. Now this one, with scientific notation, you just look at the first factor. You know, the 10 isn't included, so there's going to be 4. Remember, the last 0 after the decimal point is always significant. There's going to be 4 there. Let's put up the 4. Waiting for number 4. There it is. It's even only like 10 seconds, and it seems forever. Round each measurement to 3 significant figures. Write your answer in scientific notation. So if you're doing a calculation and you have to do rounding, then this would come in handy. And then you're going to write your answer in scientific notation. So that's going to be 87.1, or 8.7 times 10 to the 1. 8.71 times 10 to the 1, that's correct. This is going to be 4.36 times 10 to the 8th. This is going to be 1.55 times 10 to the 2 places to the right, negative 2. 2 places to the left would be positive 2. So that's very straightforward. If you have any questions with scientific notation, please ask me. That's very important. This is going to be 9.01. You got to round it to the 3 significant figures, times 10 to the 3. Okay, 3 to the left, increased by 3, so it's positive 3. This is going to be, as it's written, but it's going to be 1.78 times 10 to the negative 3. The base 10, the scientific notation, is already there, essentially. This is going to be 6.30, because the 5 is rounding the 9 to 0, and then that extra 1 is rounding the 2 to 3. So 6.30 times 10 to the 2, 2 to the left. Round each measurement in practice 3 to 1 significant figure. Write each of your answers in scientific notation. So it would be 9 times 10 to the 1. Let me just let this run. See if you can do this yourself. Okay, don't be lazy. Stop it, start it, stop it, start it. Okay, or go back and try to do it yourself. See if it makes sense. And then the 2 doesn't round to 6, so it's 6 times 10 to the 2. Perform each operation. Express your answers in the correct number of significant figures. While you're doing this, let me reaffirm what you're doing. When you're adding or subtracting, your answer has to have the same number of decimal places as the one with the fewest number of decimal places, or with the least precision. So it's going to be, the least precision is tenths place, plus or minus 0.1. So your answer has to be plus or minus 0.1. It just so happens that it's also two significant figures, but that's irrelevant. It has to do with decimal places. This is going to be to hundredths place, regardless of the answer. So it'll be 7.33 meters. And then C is coming up. And remember, when you're adding or subtracting, your answer has to have the same precision as the least precise value. When you're multiplying or dividing, your answer has to have the same number of significant figures as the measurement with the fewest number. So addition and subtraction works with decimal places, or precision, and multiplication and division works with accuracy, or the number of significant figures. So that's significant. So look at this one. This is going to have only, it's going to have, regardless of how many significant figures it has, it's going to have to tenths place, because that's what it says. So you have to round it to tenths place, so that would be 17.3, which is right. It looks like it's a typo because 17.3 is in the answer. Okay, you want to find the total of the three masses. So notice I put all the answers there. I figured it should be pretty straightforward now. So you're rounding to tenths place in number 6, and you're rounding to two significant figures in A, three significant figures in B, and three significant figures in the last one. Why is it three significant figures? Why isn't it 1? Let's take a minute and examine that. Okay, let's examine that. Hold on. See, look at it. It's 35.2 times 1 over 60. Well, 1 is one significant figure, and 60 is one significant figure. So why isn't it 6 times 10 to the negative 1? What's going on here? Well, first of all, the seconds cancel. You see that, right? Seconds cancel. And 1 over 60 is a conversion. Remember, when you multiply or divide, add or subtract measurements, 1 over 60 is a conversion. It's a factor of 1. Factors of 1 don't count in the total count of decimal places and significant figures. So the rule is, when you multiply or divide, add or subtract measurements, you have those rules. When you add or subtract measurements, your answer has to have the same number of decimal places as the measurement with the fewest decimal places, or the value with the least precision. When you're multiplying or dividing, your answer has to have the same accuracy as the least accurate value, or the fewest number, the measurement with the fewest number of significant figures. If you're converting a measurement to different units, kilometers to meters, or kilometers to nanometers, or whatever it is, you simply maintain the number of significant figures you started with. Very important distinction. Please beware of that. Calculate the volume of a warehouse that has inside dimensions of 22.4 meters by 11.3 meters by 5.2 meters. Now, this is going to be a product of length times width times height. Now, do you see that it's going to be 3 significant figures times 3 significant figures times 2 significant figures? So the answer is going to have 2 significant figures. And you'll see that that's going to be the answer. Right. So it's going to be 11.3 times 10 to the 3 meters cubed. Meters times meters is also meters cubed, and 2 significant figures. A key concept: how do measurements relate to experimental science? Well, if something's being experimented on, you have to take measurements. Making correct measurements is fundamental to experimental science. The whole concept of measurement. So if you have measurements, you have accuracy, precision, significant figures, etc. Next, number 10. Key concept: how are accuracy and precision evaluated? Well, we spent at least 2.5 weeks now on accuracy and precision, but giving you the book definition, You would say accuracy is measure value compared to the correct values, and precision is comparing more than one measurement. Or simply, accuracy is significant figures, and precision is the decimal place. Look it up and compare those answers. Why must a given measurement always be reported to the correct number of significant figures? Because, again, just as I said, the significant figures is proportional to the accuracy. The significant figures is in a calculated answer often depend on the number of significant figures of the measurements used in the calculation. So, what does that mean in simpler terms? Well, the answer says again, the significant figures in a calculated answer often depend on the number of significant figures of the measurements used in the calculation. Well, it's not often, it always does, because the number of significant figures is a measure of accuracy. The greater the number of significant figures, the greater the accuracy, and vice versa. Your calculation must be based on the least accurate value used in the calculation, where the least accurate value is defined by the least number of significant figures generated by a measurement. How does the precision of a calculated answer compare to the precision of the measurements used to obtain it? The answer, again, must have the same precision as the least precise value used in the calculation. A calculated answer cannot be more precise than the least precise measurement used in the calculation. Ergo, what I just said. Okay. Let's continue. Next, a technician experimentally determined the boiling point of octane to be 124.1 degrees Celsius. The actual boiling point of octane is 125.7 degrees Celsius. Calculate the error. Well, it's going to be 1.6 or 1.3%. In other words, you wouldn't really say negative 1.6 because it's really absolute value, but the book will say negative 1.6, fair enough, and then it would be 1.6 divided by what it should be, and that's 125.7. Determine the number of significant figures in each of the following. Okay. Again, number 13, you do it the same way we did the lab. Okay. 11 soccer players. That's going to be an infinite number of significant figures because it's a enclosed quantity, each soccer player. Okay, it's not a measurement, so it's unlimited or infinite number of soccer players. Let's change the timing on these because these will be pretty go pretty quickly. We'll do one more and then we'll change the timing. That's going to be 5 significant figures because it is a measurement using an instrument. So it'll be 5 significant figures. So that would be 5 significant figures, as I said. That would be 3 significant figures. The next one would be 3 significant figures. And E would be, there is no E. Solve the following and express each answer in scientific notation and to the correct number of significant figures. Okay, 2 significant figures. And in scientific notation, it would be 6.6 times 10 to the 4. Just put it in your calculator. Okay? 6.6 times 10 to the 4. That would be 7.2 divided by 1.8 is going to be around between 1 and 10. So it'll be 2 significant figures, 4 times 10 to the negative 7. Okay? The next one would be, it's hard to read. It's kind of small, but it looks like it would be 10 to the 7. Yeah, that's right, 10 to the 7. Then D would be, that'll be minus, so looks like a minus sign there. So you have to change those. Remind me to answer that in class. If you just put that into a calculator and use parentheses, that would be easy, but I'll explain that in class. That's going to be times, so it'll be 2 significant figures, and it'll be times 10 to the 14. Okay? And I'll talk about D in class, remind me. Liquid nitrogen boils at 77.2 Kelvin. What is the temperature in degrees Celsius? So remember the equation. It's always the degree Kelvin minus 273. So it would be 196. Okay, easy. Next. So 77.2 minus 273, or 273.15. All right, number 17. The element silver melts at 960.8 degrees Celsius and boils at 2,212 degrees Celsius. Express these temperatures in Kelvin. So how would you do that? Well, the melting point would be 1234 Kelvin, and the boiling points would be 2485 Kelvin. So you're adding, instead of subtracting, you're adding 273 to each of those temperatures. Which 5 SI base units are commonly used in chemistry? Which SI, System International base units, are commonly used in chemistry? Well, the first one is M, and that stands for meters. Metros, meters. That's going to be the first. The next one is going to be kilogram, and that's for mass. Meters is for length. Kilograms is for mass. We mainly use grams, which is the derivation, which is derived unit. K is temperature, and that is going to be Kelvin, named after Professor Kelvin. The guy's last name was Kelvin, and K is for Kelvin. And then the next one is going to be seconds. That's time. Time is seconds. So the SI unit for time is seconds, and the abbreviation is an S. Next one is a little bit weird, and we really haven't spoken about it, but you may have studied it prior, and that's MOL. Doesn't stand for molecule, it stands for moles. There's 6.02 times 10 to the 23rd particles in a mole. Which metric units are commonly used to measure length, volume, mass, temperature, and energy? So the first one, length, would be centimeters. Those are the common metric units. Now remember, this isn't the SI, this is common. Remember, meters is the metric. So length would be centimeters. Volume, it could be milliliters, it could be liters, it could be a variety of things. So length is also meters, centimeters, meters. I'm not sure there's going to be anything else there. Let's speed this up just a little bit. Kilometers is also used, where meters is the SI value. So let's speed this up just a little bit. Next is volume. Volume, we have a few. Liters is important. What's next? Milliliters is probably the dominant one for lab. Cubic centimeters, same as milliliters. Milliliters is just easier. That's microliters. And mass is going to be kilograms. We don't use kilograms. We use grams a lot in chemistry. Milligrams we also use in chemistry. Micrometers. That should be micrograms possibly there. That's a mistake. Temperature, degrees Celsius, and Kelvin. We don't use Fahrenheit in chemistry. Energy is joules. Calories, those two we use a lot. Name the quantity measured by each of the 7 SI base units and give the SI symbol of the unit. Let's see what that is. Interesting, as they say when the plot's about to thicken. Length is meter. I'm not sure where this is going. Let's see what else is they're saying here. Let's speed this up a little bit. This is mass, kilograms. Name the quantity measured by each of the 7 SI base units and give the SI symbol. Interesting. Temperature, Kelvin. Very interesting. And then time is seconds. We've been down this road before. Amount of substance is a mole. It's an interesting way of putting it. luminous intensity, candela, electric current, ampere. Okay, very good. What is the symbol and meaning of each prefix? Very interesting, as they say when the plot's about to thicken. Very interesting. Let's see. What is the symbol and meaning of each of the following prefixes? What is the meaning of each prefix? You should know these. Hint. Milli is thousandth. M for milli. Thousandth. Nano, N, you've heard that, nanotechnology. That is billionth, 10 to the ninth, negative ninth of a unit. Deci, decimeter, D, and that's going to be 10 to the negative first, or tenth. Centi, cent, 100 cents in a dollar. That's going to be hundredth. List the following units in order of the smallest to largest. From largest to smallest. That's going to be cubic meter. And then let's see, centiliter, a liter. And then looks like deciliter, then centiliter, then milliliter, then microliter. Let's see what happens. Let's see as the plot is about to thicken. Okay. Cubic meters, liters, deciliters, centiliters, milliliters, and microliters. Perfect. What is the volume of a paperback book? 2112 by 3.5. Well, two significant figures, certainly. And it's going to be 8.8, two significant figures, times 10 to the 2 cubic centimeters. Okay, number 24, here we go. State the difference between mass and weight. Mass is the quantity of matter. Weight is the quantity of matter in a gravity field. Mass is a measure of the amount of matter in an object, and weight is the measure of force of gravity on a quantity of matter. It's exactly what I said. But putting it in slightly different terms, I kind of sound a little bit like a physics teacher there for a moment. I apologize. Okay, what is the relationship between Celsius and kelvins? Well, the relationship is actually a mathematical equation. It's degrees Celsius equals Kelvin minus 273. If I have Celsius, let's say I have 0 degrees Celsius, I would add 273. So 0 degrees Celsius is 273. So 100 degrees Celsius would be 373. So it depends on which way you're going. But the degree Celsius is the same as the Kelvin. You don't say degree Kelvin, but that the two graduations are exactly the same size. Okay. Surgical instruments may be sterilized by heating at 170 degrees Celsius for 1.5 hours. Convert 170 Celsius to kelvins. You're going to add 273, and the answer will be 443 Kelvin. Again, maintaining the number of significant figures because it's a conversion. The relationship between joules and calories, they won't say that here, they'll say something different, but we usually say 1 calorie is 4.18 joules, or 1 joule is 0.2390 calories. Either one is fine. They're both a conversion. How many minutes are there in exactly 1 week? So you would just do a dimensional analysis and say 1 week, 7 days, then you'd say 24 hours in a day, then you'd say 3,600 seconds in an hour. How many seconds are there in how many seconds are in exactly a 40-hour work week? It's a little weird, a little tough there. So it's 1.44000 times 10 to the 5 seconds. I'm not sure you need all those significant figures, but either way. An experiment requires that each student use 8.5 centimeter length of magnesium ribbon. How many students can do the experiment if there is a 570 centimeter length of magnesium ribbon available? So it would be 570 centimeters, that's the length, 8.5 each, so you divide 570 divided by 8.5, and you round to the nearest student, and you get 67 students. Pretty easy, easy peasy. Next, number 31. Let's speed this up a little bit. A 1 degree increase on a Celsius scale is equivalent to 1.8 degree increase on the Fahrenheit scale. If a temperature increase by 48 degrees Celsius, what is the corresponding temperature increase on the Fahrenheit scale? Well, you multiply by 1.8, that's what you multiply the Celsius by, and then you add 32 degrees to make it 86.4 degrees Fahrenheit. You apply the formula that we derived in class. Using the tables from this chapter, convert the following. Now remember, this is just base 10. This is decimals. This is all base 10 conversions. So you're going to multiply, you're going to move the decimal point 3 places to the right, so it'll be 44 meters. It'll be 44 meters. And then what you can do is you can correct the value. For instance, 4.4 times 10 to the negative 2 times 10 to the third is 10 to the 1. So that would be make it 44. This you're going to move 3 places the other way, or it would be negative 3. 4.6 times 10 to the negative 3. Next, C. Or maybe there's just 2, yes. So this you're going to make 2 places to the right, which will be 10.7 centigrams. And then 33, more conversions where you're moving the decimal point back and forth, or simply multiplying through by base 10. Here you're going to be moving, same thing as milliliters, moving the decimal point 3 places to the left, or 1.5 times 10 to the negative 2, same thing. All right, so, or 0.015. Here you're moving it 3 places to the left, or 7, or times 10 to the negative 3, 7.38 times 10 to the negative 3, either way. C. You see how we're moving the decimal, just simply moving the decimal point? This is going to be 6.7 times 10 to the positive 3, because you're going from large to small, which will be a large value, or 6.7 times 10 to the 3 milliseconds. So you get used to, you just have to practice, and maybe I'll make up a worksheet so it'll make things a little bit simpler. Here we're going to, it would be 94.5 times 10 to the 6th, or 9.45 times 10 to the 7th micrograms, because there's 10 to the 6th micrograms in a gram. The radius of a potassium atom is 0.227 nanometers. Express this radius in centimeters. So there's going to be 10 to the 9th and 10 to the 2, so it would be 2.27 times 10 to the negative 8, because of how you're moving the decimal point. Again, very simple. These are very simple conversions. Please ask me in class if there's any question on these. The diameter of Earth is 1.3 times 10 to the 4 kilometers. What is the diameter in decimeters? If it were meters, it would be here I'm actually showing you where you're getting rid of kilometers and going to decimeters. There's 10 to the third meters in a kilometer, or 10 to the fourth decimeters, because there's 10 decimeters in a meter and then 1,000 meters in a kilometer. And that would be times 10 to the eighth decimeters. 10 to the fourth times 10 to the fourth is 10 to the eighth. 1.3, conversion, maintain number of significant figures, very basic. Gold has a density of 19.3 grams per cubic centimeter. What is the density in kilograms per cubic meter? So you would you'd convert grams to kilograms and cubic centimeters to cubic meters. I think I actually did this one out as well, possibly not, but either way, it's very, very, very simple to do. And let's see what the answer says. Yeah, here we go. So I am going to multiply by cubic centimeters, divide by meters, and then divide by grams and multiply by kilograms. So do the math. 10 to the 6th divided by 10 to the 3rd is 10 to the 3rd. So it'd be 19.3 times 10 to the 3rd kilograms per cubic meters, or 1.93 times 10 to the 4th kilograms per cubic meter. Okay? So just consider the math there. There are 7 times 10 to the 6 red blood cells, RBC, in 1 cubic millimeter of blood. How many blood cells are in 1 liter of blood? So it would be 7 times 10 to the 6th over 1 equals how many in the liter. So you'd have to change the units of liters to cubic centimeters, cubic millimeters, or vice versa, and you get 7 trillion, 7 times 10 to the 12th red blood cells per liter. Okay, let's take a break. You'll never know I was gone. Key concepts. What happens to the numerical value of a measurement that is multiplied by a conversion factor? Absolutely nothing. It's a factor of 1. What happens to the actual size or the apparent size of the quantity? What happens to the actual size of the quantity? But I think they meant apparent size of the quantity. Now, the numerical value and the units changes. The numerical value does not change. The actual size does not change. The numerical value remains the same. The actual size does not change because you're multiplying it by an equivalent. It apparently has changed. It apparently changes, but it actually does not, so I completely disagree. We'll talk more about that in class. Why is dimensional analysis useful? Well, the way they consider dimensional analysis, although I disagree with the term, dimensional analysis allows you to multiply a value by a factor of 1 or an equivalence to maintain the integrity of the original value. In other words, the value really is the same. 1 meter equals 1,000. 1 meter equals 1,000 millimeters, so it remains the same. Dimensional analysis provides an alternative approach to problem solving. That's true, but again, I'm not a great fan of the term dimensional analysis. Either way, you're multiplying it by an equivalence but you're maintaining the original value of the material. What types of problems can be solved using dimensional analysis? Well, essentially conversion problems, where I have to convert meters into millimeters, or if I have density given in grams per cubic centimeters and I want to convert it into kilograms per cubic meter, whatever the case may be. Generally, it's considered that you use dimensional analysis for conversion problems. What conversion factor would you use to convert between these pairs of units? 60 minutes equals 1 hour, or 60 minutes over 1 hour. 1 hour over 60 minutes. Well, if you're converting from minutes to hours, I guess you would put it in the denominator, unless the minutes were in the numerator. Grams to milliliters, you would put it 1,000 milligrams over 1 gram. And C, you would put cubic decimeters to milliliters. Cubic decimeters to milliliters. Well, it would be 1,000 milliliters in 1 cubic decimeter. A cubic decimeter is actually a liter. Make the following conversions. Express your answers in standard exponential form. That would be 14.8 times 10 to the 6th micrograms, or adjust that to 10 to the 7th micrograms. That's actually considered scientific notation. That would be 3.72 times 10 to the 3rd, or 0. 3.72 times 10 to the 0 grams. -3 plus 3 is 0. 66.3 liters to cubic centimeters, so that would be 66.3 times 10 to the 3rd, and then correct it for standard form or scientific notation. Next. An atom of gold has a mass of 3.271 times 10 to the -21 grams. How many atoms of gold are in 5 grams of gold? Let's see what that says. Hold on. Well, personally, I would set up a proportional relationship, meaning 1 atom of gold over 3.271 times 10 to the 22 grams equals X atoms over 5 grams. And the answer would be cross multiply and divide 1.53 times 10 to the 22 atoms of gold. I wouldn't use dimensional analysis in order to solve the problem. I would just use very basic proportional relationship, which actually shows you more the chemistry going on than dimensional analysis. Convert the following, express your answer in scientific notation. Right, so you're going to move the decimal point 3 places to the left, so it'll be 7.5 times 10 to the 1 kilojoules. Okay, because kilo is 1,000, 10 to the 3rd, etc. Okay, next, let's do 3.9 times 10 to the 5th milligrams to decigrams, so that's going to be 100, 10 squared, so it's going to be 3.9 times 10 to the 3. Next, you're going to say deciliters to microliters, so that's going to be 10 to the 5th, so that's going to be 10 to the 1. That's not 101, that's 2.21 times 10 to the 1 microliters. Light travels at a speed of 3 times 10 to the 10 centimeters per second. What is the speed of light in kilometers per hour? So you're going to change centimeters to kilometers and seconds to hours, so that's going to be 1.08 times 10 to the 9 kilometers per hour. That's pretty amazing, actually. A student finds a shiny piece of metal that she thinks is aluminum. In the lab, she determines that the metal has a volume of 245 cubic centimeters and a mass of 612 grams. Calculate the density. Is the metal aluminum? Well, that's going to be the equation, density equals mass divided by volume. You put in 612 for the mass, 612 grams for the mass, and 245 cubic centimeters for the volume. Put it on your calculator, and you're going to get something over 2. And the answer is 2.5 grams per cubic centimeter. The answer is no, but you're assuming there's not some experimental error. The answer would be 2.7 for aluminum. It says a bar of silver has a mass of 68 grams and a volume of 6.48 cubic centimeters. What is the density? Well, the equation is D equals M over V. And so then what you do is you'll plug in for M and you'll plug in for V as given. So it's going to be 68 divided by 6.48, 3 significant figures in the numerator, 3 in the denominator, and therefore you'll have 3 in the answer, and the answer is 10.5 grams per cubic centimeter. Pretty easy. Next, use dimensional analysis and the given densities to make the following conversions. All right, A, 4.8 grams of boron to cubic centimeters of boron. The density of boron is 2.34 grams per cubic centimeter, and you're simply going to multiply 14.8 grams by the density of cubic centimeters over 2.34 grams. That's a equivalent, and you cancel the grams, and you'll be left with 14.8 divided by 2.34 is 6.32 cubic centimeters. And that's what's left over because the grams will disappear. And that is using dimensional analysis to take on a density problem. B, you have 4.62 grams of mercury to cubic centimeters of mercury. The density of mercury is 13.5 grams per cubic centimeter. The same exact process, mass times the reciprocal of density, or M over D, either way, and you simply cancel the grams and you're left with cubic centimeters, and it's 0.342 cubic centimeters would be the answer. So you have 3 significant figures divided by 3 significant figures. So 6.32 cubic centimeters is the answer to A, and 0.342 cubic centimeters is the answer to B. Right. Rework the preceding problems by applying the following equation. We're not going to do that. We're simply going to look at the equations relative to this. D equals M over V for mass over volume. And then if I want to look at other equations relative to density, volume is mass over density, and I could use either one. I could use dimensional analysis, the equations, it does not matter, or the mass equals the density times the volume. Next, it says, what determines the density of the object? Well, the quotient of mass over volume, but let's see what the answer says. Well, it says that density is an intensive property that depends only on the composition of a substance, not on the size of the sample. Density equals mass over volume. An intensive property is a characteristic physical property, such as the 100 degrees Celsius is the boiling point of water. How does density vary with temperature? Well, density will change. Density tends to decrease when temperature increases, with the exception of a certain range of water, which we'll talk about later in the text. A weather balloon is inflated to a volume of 2.2 times 10 to the third liters with 37.4 grams of helium. What is the density of helium in grams per liter? So it'll be 37.4 divided by 2,200 liters, and that answer will be very small, because the density of helium is very small. And the density is 1.7 times 10 to the negative 2, that's a negative 2 grams per liter. And that's why helium balloons float in air, because it's much less dense than air. It says a 68-gram bar of gold is cut into 3 equal pieces. How does the density of each piece compare to the density of the original gold bar? Well, the whole concept is that density is an intensive property of matter, or a characteristic physical property. The density of a small piece of gold is the density of all of gold. And it says all the densities are equal, and that's quite true. A plastic ball with a volume of 19.7 cubic centimeters has a mass of 15.8 grams. Would this ball sink or float in a container of gasoline? Well, what you'd have to do is you'd have to determine the density of the plastic ball and compare it to the density of gasoline. It would sink because the density of the ball is 0.802, and it's greater than the density of gasoline. You just simply calculate the density and then look up the density of gasoline and answer the question. Very straightforward. Next, number 55. What is the volume in cubic centimeters of a sample of cough syrup that has a mass of 50 grams? The density of cough syrup is 0.950 grams per cubic centimeter. And you know that the volume, well, it would be mass over density equals volume. So 50 divided by 0.950 will equal 52.6. Volume equals mass divided by density. Very simple equation. 3 centimeter figures divided by 3 centimeter figures is 3 centimeter figures. What is the mass in kilograms of 14.0 liters of gasoline? Assume that the density of gasoline is 0.680 grams per centimeter. For this example, you're going to have to make some conversions. You're going to have to convert, I think the easiest one would be to convert 14 liters into milliliters. So you would multiply by 1,000 or move the decimal point to the right. So it would become 14,000 milliliters. Now 1 milliliter equals 1 cubic centimeter, so you don't have to convert the density. So 0.68, it would be 0.68 times 14,000. And that would be the number of grams. Now, they're going to report the density in kilograms. So then you move the decimal point back to the left. So let's see what the answer is and see if it makes sense relative to the conversion. And the answer is 9.52 kilograms. So that would be 9,520 grams. And that makes sense. 0.68 times 14,000 would be 9,520. Then that would be the number of grams. Then move the decimal point back to the left, and 9,520 grams becomes 9.52 kilograms. So remember to make the conversion of liters, 14 liters, to milliliters, and understand that 1 cubic centimeter is 1 milliliter. 3 students made multiple weighings of a copper cylinder, each using a different balance. Describe the accuracy and precision of each student's measurements if the correct mass of the cylinder is 47.32. Well, we've got to really, when we look at this, we've got to look at the last 2 decimal places, the tenths and the hundredths. So we see that Lisa is inaccurate and imprecise. Lamont is, I think, the most accurate and most precise. And Leanne, I think, is also accurate and imprecise, but she's probably going to be listed as inaccurate and imprecise. So keep that in mind when we look at the answers. Okay, Lisa is inaccurate and imprecise. That makes sense. that the third weighing is pretty off, actually. Lamont is going to be accurate and precise. If you look at the original value, 47.32, and then Leanne, they're very high. You know, the hundredth place is very high. It's almost 48, actually. So that would be inaccurate but precise, because they are close. How many significant figures are in each underlined measurement? Now, don't forget, it can be infinite, the value. 60 seconds equals 1 minute, and 60, that's going to be infinite or unlimited, however you want to say it. Infinite here. And then B, next, B is next. 47.70, that's 4 significant figures. The non-zero numbers and the 0, that's a final digit to the right of the decimal. So that's 4 significant figures. And the non-zero numbers, of course. Don't forget the conversion factors are generally considered to be infinite. So 1 kilometer equals 1,000 meters. That's also infinite. And then we have next, as the plot thickens, 25 computers. That's also infinite. It's an infinite value because they're kind of, I like to think of them as being encapsulated. They're not really measured. There's no estimated place value there. Round off each of these measurements to 3 significant figures, and also put it in scientific notation. I'm not sure it's this one or the next one that I did that. So that would be 98.5 or 9.85 times 10 to the 1 would be the answer there. Here we go. Shall we speed this up a little bit? I think we shall. All right, hold on. Okay, so this would be 7.63 times 10 to the negative 4. Okay, 7.63 times 10 to the negative 4. This would be 5.70 times 10 to the 1. Next, D would be 12.2 or 1.22 times 10 to the 1. This is even seems slow as well. Next, round off each of the answers correctly. So we got to look at the number of significant figures. This is going to be decimal places. So it's going to be 43 or 4.3 times 10 to the 1. B is going to be, it's minus, so 10th place, so 225.8, and that'll be 2.258 times 10 to the 2. As the plot thickens, don't forget it's the least accurate, the least precise. This is the least accurate, so it's going to be 92.0 or 9.20 times 10 to the 1. 3 significant figures because of the denominator there. This is going to be 3 significant figures, so it'll be 32.4 or 3.24 times 10 to the 1, and that'll be cubic meters. Remember, that's accuracy, it's multiplication. How are error and percent error of a measurement calculated? The error is the difference between the experimental value and the accepted value. The percent error is divided, the percent error is the error divided by the accepted value times 100. Very important for lab work. List the SI base unit of measurement for each of these quantities. List the SI unit. Time is seconds. Time is seconds. Length is meters. Temperature is Kelvin. Mass is kilogram. And that's it. Order these units from smallest to largest. Well, the smallest is going to be picometers, and then it's going to be nanometers, and then it's going to be micro, and then it's going to be milli, then centi. Those are the 10 to the 12th, negative 12th is pico, 10 to the negative 9th is nano, 10 to the negative 6th is micro, 10 to the negative 3 is milli, 10 to the negative 2 is centi, then 10 to the negative 1 is deci, and then meters is just 1, and then kilometers is 10 to the 3, and that's the order and the units. Let's see if you can continue as I finish speaking. I'll come back in a moment. Just having some coffee in the morning in my classroom. It is 6:14 in the morning. All is quiet on the Western Front here, and we're having a lot of fun. It'll be a very important video for you to watch this weekend. Hopefully it'll be up by today. So centi now, just deci, that's negative 1 again, as I said. Meters is just 1, and then kilo is 10 to the 3rd. All right. That's only 10 seconds per slide, so it's pretty amazing how that works. Seems like much longer period of time. And then maybe it's 15 seconds. I think it's 10. Yeah, it's 10 seconds. Okay, so that's it. Let's go to the next problem. We'll cut this one off soon. All right, we're going to measure each of the following dimensions using a unit with the appropriate prefix. Meaning, you want to try not to write a number too small. That's why you're going to use a prefix. That's the whole idea. So that letter I, if I measure the height of that, that's going to be 2.4 millimeters. See how it's kind of within units? It's kind of within 1 or 2, between 1 and 10. Let's see, what's next? The width of table 3.3 from the book? Probably centimeters, I'm guessing. That's a guess. Centimeters, 14.33. If it were millimeters, what would it be? It would be 143.3. If it were meters, it would be 0.14, right? The height of the page, well, the height of the page is going to be probably, if you look at your book, it'll be about that, 27.5, about 11 inches-ish, more or less. Probably not quite. The melting point of silver is 962 degrees Celsius, very high, but not really that high for metal. Express this temperature in Kelvin. So you're going to add 273 to that, and the answer will be 1235 Kelvin. 1235 Kelvin. 962 plus 270 is 1235. What is the name given to a ratio of two equivalent measurements? What is the name given to the ratio of two equivalent measurements? Conversion factor. 60 seconds equals 1 minute, so I could put 60 over 1 minute or 1 minute over 60. What must be true for a ratio of two measurements to be a conversion factor? They must be equivalent. equal in a sense. But the reason they call it equivalent is because it really doesn't look equal. It's kind of weird looking. 1 meter equals 100 centimeters. How do you know which unit to put of conversion must be in the denominator? The one you want to cancel in the numerator. The unit of conversion factor in the denominator must be identical to the unit given measurement or the previous conversion factor, unless you're converting something in the denominator and then you put it in the numerator. So that's not a great answer. Make the following conversions. Okay, remember your base 10. 157 centiseconds to seconds. So you're going to move the decimal point over to the left. So it'll be 1.57. 2 places because it's centi. 10 to the 2, 10 to the negative 2. So you're going to move it 2 places to the left. Liters to milliliters, you're going to move it 3 places to the right. So 427, and then the appropriate number of zeros. And that'll be, in terms of scientific notation, if you're going to move it to the left between 4 and 2, you've got to multiply by 10 to the 4. 261 nanometers to millimeters. Nano is -9 and milli is -3, so that'll be -6. So that'll be 2.61 times 10 to the -4 millimeters. Okay, next it would be 0.065 kilometers to centimeters. So it'll be 10 to the 4, because kilometers is 10 to the third, deci is 10 to the -1. So if you're going to move it over to the 5, between the 5 and the 6, it will be 6.5 times 10 to the -2. Okay, remember, let's do some of these in class. So centigrams to kilograms, that'll be -5, so it'll be 642 times 10 to the -5. Come back 2 to the left, it'll be -3. Right. Next, so it'll be 6.42 times 10 to the -3. Okay, the plot thickens. So you're going to go from centigrams to nanograms. That's going to be +7, so it'll be 10 to the 9th, 8.25 times 10 to the 9th. And that's correct in nanograms. Okay, let's continue. As they say, when the plot thickens, the plot is about to thicken. Make the following conversions. Something completely different now in number 71. So let's make some conversions. 0.44 milliliters per minute to microliters per second. So you're going to change the milliliters to microliters and the minutes to seconds. So it's going to be 7.3 microliters per second. Again, we'll do some in class, remind me. I'll just let this one run, see if your answers are correct. I'll let this run to the end, and then we'll do some more work. Kilograms per liter to grams per cubic meter. So 1.54 grams per cubic meter. Okay, interesting that it's the same number, 1.54. How is that true? How many milliliters are contained in a cubic meter? Well, there are 1,000 liters in a cubic meter, a metric ton. Each liter is a kilogram. And so if each liter is 1,000 milliliters, 1,000 times 1,000 would be 10 to the 6th. 10 to the 3rd times 10 to the 3rd. Apply your exponential rules. It's 10 to the 6th. 10 to the 6th milliliters in 1 cubic meter. A million. Not bad. Okay, let's continue. What else we have? Okay. Complete this table so that all the measurements in each row have the same value. Okay. So we're going to say centigrams, we're going to convert that to milligrams, grams, and kilograms. Okay, let's get started. So that's going to be 2.83 times 10 to the 2 milligrams. I hope that makes sense. Using scientific notation, it's sometimes hard to make sense of it right away. And then B is going to be 0.283 grams, and then 2.83 times 10 to the negative 4 kilograms. All right, so let's continue. I'll let you fill out the chart. This is because everything is in scientific notation. Look at number I if you haven't done that. It's just going to be probably negative, what? Grams and kilograms. It's going to get smaller. -7 maybe. Interesting. Yeah, -7. Easy peasy. The first row is the hard one because I'm giving the answer two of the answers in scientific notation. What equation is used to determine density of an object? That's a pretty quick question. I don't think we need 10 whole seconds to answer that. It's density equals mass divided by volume. It's a ratio of mass to volume, but mass to unit volume. In other words, what is the mass in 1 unit of whatever the volume would be? In chemistry, we mainly use milliliters. What would the density of a person, would the density of a person be the same on the surface of Earth and the same on the moon? Yes, neither mass nor volume of a solid or liquid changes appreciably with location. That's not altogether correct, but it's close enough. Ask me in class for extra credit. First person to ask me. And here is number 76. Let's take a look at that. A shiny gold-colored bar of metal weighing 57.3 grams has a volume of 4.7 cubic centimeters. Is the bar of metal pure gold? Well, gold is almost 20, density is almost 20 grams per cubic centimeter. It's like 19.3, so 20 times 4 is well in excess of 57, so I would say no, just by initial inspection. But what you could do is that you could do the math. So you could round 4.7 to 5, round 57 to 60, and you'd get something a bit less, and that's 12 grams per cubic centimeter, and you would say no. 3 balloons filled with neon, carbon dioxide, and hydrogen are released into the atmosphere. Use the data in table 3.6 on page 90 to describe the movement of each balloon. Well, carbon dioxide, and I will demonstrate that in class, is very heavy, and I will tell you a story. First one to ask me to tell the story will receive extra credit during class, not before class, after the bell, after I take roll. Timing is everything. The carbon dioxide filled balloon would sink. The neon and hydrogen filled balloons would rise. The hydrogen at a much faster rate because it's very low density. It's the lowest density gas. It's the smallest element on the periodic table. So it makes perfect sense. All right. Let's continue. Let's change the timing of some of these questions. List 2 possible reasons for reporting precise but inaccurate measurements. Precise but inaccurate. That's interesting. Improper calibration or improper use of the measuring device. Improper calibration is probably the best answer. You're assuming people know how to use the equipment you're using in lab. If not, you have to teach them how to use it. Rank these numbers from smallest to largest. This is a little bit of a practice between scientific notation and non-scientific notation. So this is going to take a few minutes, so let's change the timing on this. So I can spot the largest and the smallest right off the bat. 5.1 times 10 to the negative 3. But you got to double check D. Well, D is 5.7 times 10 to the negative 3, so that's a little larger. So the 5.1 times 10 to the negative 3 is definitely the smallest. The largest is going to be 10 to the 4th. Then 10 to the 3rd would be next smallest. So then 10 to the 2nd, then 10 to the negative 2, then 10 to the, then 5.0057, and then 5.1. So from smallest to largest, it would be E, would be the smallest, then D, then work our way up, then C, then F, and then B, and then A would be the largest. So let's see if that's correct. I'm going to speed up. Instead of 10 seconds for each, I'm going to speed up the answers. So it would be E would be correct, then D, then C, I said that, then F, then B, and then A. A is the largest. Comment on accuracy and precision of these basketball free throw shooters. Okay, so we're going to look at some data, and let's see what we can see. 99 out of 100 shots are made. Pretty accurate, pretty precise, I would say. However, the book says accurate and precise, and that is my final answer. Okay, going for $60,000 here. B is going to be 99 out of 100 shots hit the front of the rim and bounce off. Very inaccurate, but extremely precise. Inaccurate, but precise. C, it is going to be 33 out of 100 shots are made, the rest miss. Inaccurate, imprecise. Okay, that was pretty straightforward. We're waiting for the, and that is my final answer. Okay, let's go to the next group of problems. Okay, Fahrenheit is the third temperature scale that we really don't use unless you're in America. Plot the data in the table and use the graph to derive an equation for the relationship between Fahrenheit and Celsius temperature scales. And there's the equation. Now, I want you to plot the data. Very similar to what we did before. And you find the slope and you find the y-intercept, etc. And that is going to be the question stated again. You can put your graph there. You can insert your graph. And here's the data table. So you want to graph each point. Now, graph degree Celsius on the x-axis and degree Fahrenheit on the y-axis. And there's your 2 points. So you have 5 points, you graph them, and then you use your techniques to write the equation y equals mx plus b. Look at the video if you need help. I made a video on deriving that equation, so that would be important for you to do. Which would melt first? Germanium with a melting point of 1210 Kelvin, or gold with a melting point of 1064 degrees Celsius? Well, it would be germanium. You have to convert if you want to be able to read it, either both to Kelvin or degrees Celsius, and you can see which one will melt first. Write the 6 conversion factors involving these. Very simple. You're just going to, it will be, for instance, 1 gram over 100 centigrams, etc. And then write the reciprocal. They're both used for canceling, etc. And those are your 6 conversion factors. I'm not going to spend a lot of time on it. Very simple, very straightforward. A 2 kilogram sample of bituminous coal, that's soft coal, is composed of 1.3 kilograms of carbon, 0.20 kilograms of ash, and 0.15 kilograms of water, and 0.35 kilograms of volatile gas-forming material. Using this information, determine how many kilograms of carbon are in 125 kilograms of this coal. Well, what you're going to do is you're going to set up a proportional relationship in order to make the calculation. So let's talk about that just for a moment. So it would be 2 kilograms over 1.3 kilograms, because every 2 kilograms gives you 1.3 kilograms of carbon. And so you would say you would say 125 kilograms of carbon over X. So you would say 2 kilograms over 1.3 kilograms and 125 kilograms over X. So write that down and see if you can calculate the answer. See if you can do it before the answer comes up on the scale. So again, it would be 2 over 1.3 equals 125 over X. Cross multiply and divide to solve for a proportional relationship. 7th grade math, I think you can do it. Yes, 81.3 kilograms. That's 81.3 kilograms. All right, let's go to the next one. A piece of wood sinks in ethanol but floats in gasoline. Give a range of possible densities for the wood. Well, you would put the density of ethanol and the density of gasoline, and it's somewhere in between, and that's exactly what they did. 0.69 to 0.789. Now, be careful. Some wood is more dense than others, so you have to check out the piece of wood. The density of dry air measured at 25 degrees Celsius is 1.19 times 10 to the negative 3 grams per cubic centimeter. What is the volume of 50 grams of air? Apply the equation, V equals m over d, and that's what you get. Okay, next. Simple equation, plug it in, use your calculator. A flask can hold 158 grams of water at 4 degrees Celsius, the most dense that water is, and only 127 grams of ethanol at the same temperature. What is the density of the ethanol? 0.804 grams per cubic centimeter. Ask me to do that in class. First one to ask me gets extra credit. A watch loses 0.15 seconds every minute. How many minutes will the watch lose in one day? You've got to do a dimensional analysis, calculate the number of minutes in a day, and then multiply by 0.15 seconds. You get 3.6 minutes lost. Okay. Now, a tank measuring 28.6 by 73 by 0.72 meters is filled with olive oil. The oil in the tank has a mass of 1.38 times 10 to the 4th grams. What is the density of the olive oil in grams per liter? So you're going to have to do quite a bit of dimensional analysis here. First one to ask me to do that in class will receive some extra credit. 0.92 grams per liter. Notice that it is less than water, so the olive oil will float on water. Next, number 90. Okay, alkanes are a class of molecules that have the general formula CnH2n plus 2, such as octane, single bonds, where n is an integer whole number. The table below on the next slide gives the boiling points for the first 5 alkanes with an odd number of carbon atoms. Using the table, construct a graph with number of carbon atoms on the x-axis. What are the approximate boiling points for the alkanes below? Now, again, this is going to be done in class. This is going to be a class assignment with a couple of other things. So here are here's the chart, the number of carbons and the boiling points, etc. So C2, we're going to find from the graph, are going to be, C2 is negative 90, C4 is 0, C6 is 70, C8 is 125. Okay. Now, what is the approximate increase in boiling point per additional carbon atom in these alkanes? What is the approximate increase? From C1 to C9, the increase is approximately 39 degrees Celsius per additional carbon. Over the range C3 through C9, the increase is approximately 32 degrees Celsius per additional carbon. So that's going to make a very nice class assignment that we're going to work on. I didn't want to do the whole problem because I want to do that problem in class. Okay, didn't want to give away the farm. Earth is approximately 1.5 times 10 to the 8th kilometers from the sun. How many minutes does it take light to travel from the sun to the Earth? The speed of light is 3 times 10 to the 8th meters per second. So what we'll do is we will do it in seconds and then convert to minutes, and it's 8.3 minutes. Again, first one to ask me to do that in class, not a problem. Okay, what is the mass of a cube of aluminum that is 3 centimeters on each edge? The density of aluminum is 2.7 grams per cubic centimeter. So it's going to be 3.0 centimeters on an edge, so do the volume, do the math. And it's going to be, the mass is going to be the density times the volume, and that's, again, 73 grams. The average density of Earth is 5.52 grams per cubic centimeter. Express this density in units of kilograms per cubic decimeter, which is the same thing as a liter. Okay, so it's going to be 5.52 kilograms per cubic deciliter. You multiply grams by 1,000, you multiply cubic centimeters by 1,000, same thing as 1 is 5.52, looks the same. How many kilograms of water are needed to fill an aquarium that measures 40 by 20 by 30 centimeters? Density of water at 4 degrees is 1 gram per cubic centimeter, 24 kilograms of water total. Okay, almost finished. 14 problems left out of 108. We're doing well. Next. Is it possible for an object to lose weight, but at the same time not lose mass? Well, if you exercise and you can be the same mass, yes, the mass of an object is constant. The weight of an object varies on location. So when you're trying to lose weight, it's not really a good idea to do it by going to the moon or to Mars. So the mass is going to stay constant, but the weight will vary according to gravity. Even if you diet, you can lose fat and put muscle in there. You have a change of densities, but that has to do with volume and mass, not necessarily volume and density. Not necessarily you can't lose weight in mass. It doesn't work in dieting. Sorry. Okay, one of the first mixtures of metals called amalgams used by dentists for tooth fillings consisted of 26 grams of silver, 10.8 grams of tin, 2.4 grams of copper, and 0.8 grams of zinc. How much silver is in 25 gram sample of this amalgam? So remember that 26, it says dentists for tooth filling consisted of 26 grams of silver. So this is a little bit complicated, so let's talk about this just for a moment. So it's worded a little bit in a complicated way based on the way the other problems have been worded. So the total amount of amalgam would be 26 plus 10.8 plus 2.4 plus 0.8, and you get that total. And that total amalgam has 26 grams of silver. So it would be 26 grams of silver over that total amalgam equals X over X amount of silver over 25 grams of amalgam. So it's a little bit, you have to kind of read it more than once. Again, extra credit, first person asks me in class to do the problem will get some extra credit. Hopefully this will be up on the web before 16.3 grams is the answer before you ask me. A cheetah can run 112 kilometers per hour over a 100-meter distance. What is the speed in meters per second? So you're going to convert kilometers to meters and hours to seconds. Dimensional analysis, 31.1 meters per second. So 31.1 meters per second is pretty fast. You are hired to count the number of ducks on 3 northern lakes during the summer. In the first lake, you estimate 500,000 ducks, the second 250,000 ducks, and in the third 100,000 ducks. You write down that you have counted 850,000 ducks. As you drive away, you see 15 ducks fly in from the south and land on the third lake. Do you change the number of ducks that you report? Justify your answer. You do not change your estimate. Counting the extra 15 ducks would suggest greater precision than was used in the estimate. Because in the first 2 lakes, you didn't do that process, so you got to keep the process the same. What if ice were more dense than water? It would certainly be easier to pour water from a pitcher of ice cubes and water. Can you imagine situations of more consequence? Well, the first thing would be that the lakes would freeze solid, and water does not conduct heat very well, so as the lakes melt, they wouldn't really unfreeze. There'd be a permafreeze, much like there is in the ground in northern latitudes, and it would be possible, you'd have possible climate changes as a result of that. You'd be taking water out of the water cycle, all kinds of horrid things would happen. Why is there a range of values given for the density of gasoline on table 3.6 on page 90? Well, because gasoline is a mixture, it is not a substance. A substance, as you know, is composed only of pure material, either an element or a compound. Plot these data that show how the mass of sulfur increases with the increase in volume. Determine the density of sulfur from the slope of the line. So that's the data we're going to graph. All right, so let's graph that data. All right, here's the graph. So I plotted the mass of sulfur, y-axis, always y versus x. And now what I want to do is I want to take the slope of that line and I add a trend line, and the slope of that line is 2.0713. And using significant figures, I'm going to report 2.1 grams per cubic centimeter is the slope of that line. 102. At 20 degrees Celsius, the density of air is 1.2 grams per liter. Nitrogen's density is 1.17 grams per liter. Oxygen's density is 1.33 grams per liter. Will balloons filled with oxygen and balloons filled with nitrogen rise or sink in air? The oxygen-filled balloons will sink. The nitrogen-filled balloons will rise. But you know what? Not very much. Air is mainly a mixture of nitrogen and oxygen. Which gas is the main component? Well, for life it's oxygen, but in terms of percentages, it's easily nitrogen. Nitrogen is the weighted average density of air. The weighted average density of air is close to the density of nitrogen because it's 80% nitrogen. The mass of a cube of iron is 355 grams. Iron has a density of 7.87 grams per cubic centimeter. What is the mass of a cube of lead that has the same dimensions? So mass equals density times volume. So you have to calculate the volume, which is m over d. You're going to calculate the volume, and then you're going to find the density of lead, and then you're going to multiply that times the volume, and you get, let's see, let's speed this up just a little bit. So again, you want to mass over density is going to be the volume of the iron, which is 45.1. And then you're going to look up the density of lead, and you're going to multiply the density of lead by 45.1, and the mass of lead is going to be 514 grams of lead. Okay. As we wait for the next one to come along, just remember to take this stuff seriously. If you do all the problems and you really know how to do them, not just kind of faking it, you'll do extremely well on the test. It's the first test of the year, and you really want to start off with a bang. Seawater contains 8.0 times 10 to the negative 1 centigrams of the element strontium per kilogram of seawater. Assuming that all the strontium could be recovered, how many grams of strontium could be obtained from 1 cubic meter of seawater? Assume the density of seawater is 1. It's a little more than 1, but fair enough. Okay, so how do you do it? Well, first one asked me in class, will get some extra credit. Maybe I'll do that one today. Who knows? 8 grams of strontium. See if you can get that one. 104. Not a problem you have to do, but a problem you really should do. That would really be very helpful for you for the test. Okay. Next. 105, as they say when the plot's about to thicken. Next. 105. The density of dry air is 1.2 grams per liter. What is the mass of air in kilograms of a room that measures 25 meters by 15 meters by 4 meters? Kind of a weird shaped room, but certainly a big room. Certainly a very big room. So what you would do is you're going to find the volume, do some dimensional analysis changes, and you're going to find that it's 1.8 times 10 to the 3 kilograms. That's a lot. That's almost 2,000 kilograms. It's a ton. So that air is pretty heavy stuff. So if you think of a hurricane and all that wind blowing and why houses blow down, that gives you a good idea of why wind can literally knock cars off the road or knock you off your feet. Different volumes of the same liquid were added to a flask on a balance. After each addition of liquid, the mass of the flask with the liquid was measured. Graph the data using mass as the dependent variable. Use the graph to answer these questions. Okay, there's the data. So you want to graph the data, which will be very important, and then you want to ask, what is the mass of the flask? What is the density of the liquid? Very good question. And here's the graph, if you can see it. I'm looking at a very small version of it, so I'm sure you can see it. And then that's the equation, the trend line equation. 1.3398 is okay, there's the question again. And here is the equation that I'm bringing forward. And then what is the mass of the flask? And what is the density of the liquid? Well, the flask is going to be the y-axis, the y-intercept, and that's going to be 85 grams, because that's really what you're starting at. So everything is above that. And the density is 1.3 grams per milliliter. Do you see why the 85 grams is there? Well, everything is being added to the flask. All those masses are being added to the flask, so you're going to have a y-intercept of 85 grams. A 34.5 gram gold nugget is dropped into a graduated cylinder containing water. By how many milliliters does the measured volume increase? The density of water is 1 gram per milliliter. The density of gold is 19.3 grams per cubic centimeter. Milliliter, cubic centimeter, same thing. Do the math. Do the math. So what's the volume? If you have 34.5 grams of gold, what volume is that going to relate to? And it's going to be 1.79 milliliters. All right, do the math. Let's go on to the next one. Equal amounts of mercury, water, and corn oil are added to a beaker. So the mercury will be on the bottom, then the water, then the corn oil on top. Describe the arrangement of layers of liquids in the beaker. Pretty common. We know that oil floats on water and mercury is very dense. So corn oil on top, water next, and then the mercury. Okay. Let's go on to B. Same question, but B now. Here's the repeat of the question. Equal amounts of mercury, water, and corn oil are added to a beaker. Let's go on to B. And it says a small sugar cube is added to the beaker. Describe its location. Describe its location. Well, the sugar cube, first of all, is going to be lighter than sugar because there's going to be air spaces within the cube. So its density is not going to be the same as sugar necessarily because you have air spaces in there. The density of the sugar is greater than the density of water and less dense than mercury. It floats between the layers of mercury and water. Yeah, but again, it's not necessarily, you'd have to do an experiment on that, and that might be your hypothesis, but a sugar cube, there's air spaces, so that would reduce the density of the sugar. What change will occur to the sugar cube over time? Well, if it's where the book says it is, it would dissolve in the water. And the water would become more dense, but not more dense than mercury. The sugar cube will dissolve in the water over time. Again, the water would become more dense, but not more dense than mercury. So the water would not change its leveling.